Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss about the properties of nanomaterials. Since we already learned many different aspects, mostly the structural aspects of nanomaterial in the last week, and we have seen that large number of surface atoms are involved in those microstructures or nanostructures. So, the properties may be different than their coarse grain counterparts. Now, one thing we should keep it in mind when we talk about nanoparticles, the nanoparticles are a size of let us say 10 to 100 nanometer, let us assume. So, measurement of any properties which require bulk sample is very difficult. And so, today we will start with one of the very difficult properties that can be measured in a nanomaterial. We will start with. So, before going to nanomaterial, I would suggest that we can recapture or let us say discuss some of the very basic fundamental of the mechanical properties of materials. The stress strain diagram provide us a very simple and very fundamental aspect of any material, which is shown in the left hand side. Here this is the strain, which is basically the length change divided by original length, and here this is the stress sigma. The typical properties that scientists observe that the stress and strain follow such a linear behavior, and after some strain value then it shows a non-linear behavior. This is a very typical plot for metals and alloys, or let us say ceramic and so on. However, this linear portion is somehow linked with their bond, means the bond strength, and from this linear part we can measure Young's modulus, and we can simply think about that how linear relationship exists in metals, alloy or ceramic. This is a part, if we unload it will come back, okay. Means this is a elastic region. In this elastic region, the stress is proportional to strain. Okay. So, this is a proportional portion and this is the proportional limit of the diagram, and this part is the elastic deformation which follow Hooke's law. So, Hooke have suggested this law, and there is a constant, it is Young's modulus E, and this E is linked with the melting temperature also. If you see, tungsten has a very high Young's modulus and very high melting temperature. Now, aluminum has a lower Young's modulus and lower melting temperature. Like polymer also have the same very low Young's modulus and very low melting temperature. So, this is very simple. Now, ceramic material has a very high Young's modulus and very high melting temperature. So, these are the very wide range of materials. However, here in case of ceramic it does not go beyond this proportional limit and material usually fail here, but metal shows some plastic deformation. Please remember that this is a stress strain plot unique for a uniaxial stress level. Uniaxial means I have a sample and simply I am putting some stress in this direction and so on. However, the non-linear portion represent the plastic deformation, means permanent deformation. It simply means if I stop the test here and unload it, the sample will after unloading will show this is the permanent deformation, okay. And the elastic recovery will takes place. So, this is a permanent deformation or permanent strain in the material. So, this flow curve is in this portion where you have permanent deformation region, and it follows a relationship which is a flow curve equation called sigma is the stress, okay, load by area, and this is the strain which is the delta L by L or length change, and there is a k is the constant flow curve constant with a strain hardening exponent n. However, one must consider that n is not constant throughout the deformation, n value changes with the percentage of the strain also, okay, because there is a presence of defect like dislocation and the dislocation multiplication occur and so on, and continuously the strain hardening exponent increases. The more number of dislocation and their mechanisms are involved in it. Now, the major shortcoming of nanoparticle to measure their, let us say, the mechanical properties is their smaller in size, because a finite size, a quite large size is necessary in order to hold the sample with a fixture or grip and then pull it to the two side, so that we can apply the stress. But in a 10 nanometer particle size, how can we apply stress? That is impossible, right. So, therefore, we need some bulk 3D shape, and maybe we can go for some consolidation of those nanoparticle, and then we can make a bigger, let us say 1 inch or 10 inch size sample, and then I can make a stress on it, that could be. On the other hand, let us think about the structure, means microstructure and structure. So, in a crystalline solid, as an example of metals alloy or ceramic, the atoms are arranged, are well organized in a lattice, and there is a region where a large number of atoms exist in this grain boundary region. So, this is a grain boundary region where the atoms are randomly arranged, okay, in the grain boundary. So, this is a disordered boundary. Now, if I make the microstructure smaller and smaller, means the grain size smaller and smaller. So, these are the region will join as the grain boundary, right. So, these are the positions of the atom where the grain boundary region is more and more, I have small size. So, the fraction of the grain boundary will increase, and now one can reach to a extreme disorder which is called as a amorphous material, where the total disorder exists. So, this is a amorphous structure. Now, the situation is similar in case of polymer also. However, we can consider a nanocrystalline material which is a mixture of crystallite or grains with a mixture of some amorphous region, okay, which is the grain boundary. An amorphous material we have discussed has a very high strength. So, if I consider a nanomaterial or let us say nanostructured material with a very small crystallite or grain size with let us say 50% of the area which is covered by a totally disordered organization of the atoms, then the strength supposed to increase. So, nanomaterial should show or expected to show very high strength, not like glassy or amorphous alloy, but at least in between the conventional microcrystalline sample and in between basically the two extremities. Okay. So, this is the general expectation. Now, in case of a polymer, mostly polymers are glassy or amorphous. However, there are semi-crystalline polymer, there are very small units which appears to be has some sort of order structure like crystallite, like spherulitic structure and so on. However, there are also fully disordered or let us say glassy polymers. So, this is valid not only for metals alloy and like our silicate glasses or window glasses has such kind of fully disordered structure, whereas glass ceramic has some crystalline structure, but we should keep it in mind that glass ceramic does not show such kind of plastic deformation. This is a unique feature for metals and alloys. Okay. So, you see that these three different kind of material has their wide range of properties, and we can always go for some composite to see the change of their behavior in terms of mechanical properties. Now, I show you some of the typical stress strain plot that has been obtained from a metal and let us say for a rubber or let us say some biological tissues. So, this is the strain and stress plot, where this is the typical metal and this is the plastic region and here this is the elastic region which we have discussed. So, this is for a metal, the red color curve, whereas the rubber shows a rubber like elasticity which is very very high, and even if you decrease the stress level or unload the sample, then it will again come back. So, this is called rubber like elasticity. So, in rubber actually these kind of segment and let us say some movement or relative movement of those segments are linked with such kind of high elastic behavior, whereas our body has collagen which is the very basic unit like a linear chains of some molecules. So, those are the collagen which is the one of the very basic unit of our body. So, they are also very very elastic in nature, because if you use a muscle and then unload your hand actually it again come back, right. So, the collagen is behave like that way. So, in all these cases the material has a very very different properties, and we will try to understand what is the effect of nano here, because the structural units if it is very very small. However, there are very very less number of stress strain plot available for collagen and so on. So, what we so far understood that if we have very small particle size we have to consolidate, and during consolidation the problem arises. The reason is that every such compacted sample or differently processed nanomaterial may have some processing artifact. A first very example of a processing artifact is the defect or porosity. Okay. So, this defect or porosity we can estimate in terms of P, which is equal to 1 minus density of the specimen with the theoretical density. And people have measured the properties like the Young's modulus or E. Okay. So, here E is the Young's modulus and E 0 is the theoretical one, okay, theoretical Young's modulus. So, if you take a example of a nanocrystalline palladium or nanocrystalline copper. So, this is the copper and this is the palladium. So, people observe that such kind of data plots are available with the porosity content. So, this is let us say 2% pore, 3%, 4% and 6% and so on. So, very little 1 or 2% porosity can decrease the Young's modulus such a low value than the theoretical one, where theoretical one was 130 and if you have 3% then it goes to 120. So, 10 and this is because of the porosity, and one can fit a straight line or a nonlinear curve which basically follows such kind of equation that the theoretical Young's modulus multiplied by 1 plus alpha 1 which is a constant in multiplied by the percentage porosity and alpha 2 p square and so on. So, this is the porosity that scales with the Young's modulus. Now, is there any effect of presence of porosity not only in terms of Young's modulus, but in case of the strength? Yes, the strength of a metal also depends on the percentage porosity. So, same material in case of copper and palladium you see there is a sharp decrease of the yield stress similar to in case of a copper. So, one should be very much careful during processing of nanomaterial, so that the processing should produce almost 100% or near theoretical density. Now, the second part comes here, that whether there is any effect of such kind of small grain size, and what is its effect on reducing the grain size on the strength. The strength in a material arises, usually it is explained in terms of dislocation pile up, like Stroh's pile up model, and we can simply think about a microcrystalline sample with a grain diameter of d. So, this is a sample with a microstructure which a equiaxed microcrystalline samples are there, grains are there, and here let us say the dislocation are piled up at the grain boundary. Okay. If we put some stresses, then this dislocation basically flows inside the grain and they piled up near the interface, because interface they cannot pass that barrier and a force is built up at the interface. So, the forces will be built up at the interface and dislocation will try to move. So, this is let us say in case of a equiaxed. However, the size scale, let us say it could be a nano range where we bring down the scale, we can dream about such a situation, or we can think about a laminated structure where the laminate, inside the laminate the similar situation dislocation will try to flow and they will pile up at the interface. Now, can we estimate the value of those obstacle that is provided due to the grain boundary, or maybe the dislocation are moving on a plane and one can put a particle and the dislocation find an obstacle on its slip plane and build up some stress. So, this will provide us a force value, a force, a very simple let us say a schematic I have shown you here, and here you see that this kind of slip plane where a force is built up which is proportional to the n is the number of such dislocation, b is the Burgers vector, and the stress different due to the build up pile up stress. So, S 0 depends on other stress than this pile up, like lattice friction stress. Lattice had itself a friction, and that friction the dislocation has to overcome, so that it can flow on a or glide on a plane, and that stress is like a S 0. Okay. Now, if you think about such kind of honeycomb like structural grain, or let us say equiax structure, or maybe such kind of bilayer spacing like a laminated structure, the situation is not different, okay, and the equations or understanding is not different, they are very similar. Now, we can find out that the force that value the obstacle provided which need to overcome required, because if slip has to transfer from this grain to this the next neighboring grain, and dislocation will flow in the neighboring grain only when the dislocation slip will transfer from one place to another place. So, grain 1 to grain 2 the slip will transfer, and the transfer require a stress transfer build up a stress, and so that the plastic deformation can occur, and this is the equation which says that n is the number of such piled up dislocation multiplied by the Burgers vector and tau minus tau 0, because we can simply from a stress we can go to the shear stress. So, ultimately the stress difference because of this build up stress is proportional with basically B by D, and we can derive, or this is a typical Hall-Petch equation which says that a stress, okay, or yield stress, so that the plastic deformation before plastic deformation to occur, so or slip transfer to occur. So, the stress is equal to sigma 0 plus k into B by D root. So, the stress scales with the 1 by root D. So, D here is the grain diameter, okay, or let us say the laminated structure or bilayer spacing. Okay. And this is a understanding, it says that if we decrease the grain size, the strength should increase, okay, from the very fundamental equation. But the question comes whether this is very new, unique to the metallurgy field. It is not, because people are doing this heat treatment called aging treatment in aluminum alloys, where there are nano rods of Al2Cu forms in such a microstructure. This is a typical aluminum matrix with the nano rod of Al2Cu, and you can see this is a scale of 50 nanometer. So, the rod diameter is something like 10 nanometer or so. So, this is so small or less than that. So, here people already find out that the Vickers hardness, which is a measure of the strength hardness. So, that basically increases when these nano rod basically form, and during coarsening also it gives a effective strengthening, where you get a optimized situation where the interparticle distance and the diameter of these rods are optimum. Okay. So, this is a situation, let us say, with a aging time and let us say aluminum 4% copper. So, strengthening material using nanomaterial is nothing new. Okay. However, we can proceed with this discussion to find some real life example how it is. So, the first example I give you is the palladium, which has a grain diameter of 14 nanometer. This is very small, or let us say a palladium with a grain diameter of 50 micrometer. This is a microcrystalline sample and this is a nanocrystalline sample. The unique observation here that the strength is definitely low as per the Hall-Petch equation that we have just learned few minutes ago, and the strength of let us say the palladium with a nanocrystalline size is very high. So, here let us say from 30 it reaches up to let us say 250 or so. This is very high. So, by just reducing the grain size, whereas the Young's modulus basically decreases in case of a nanocrystalline material, because we have already large amount of disordered atoms are present, which are not sitting in the equilibrium position. And if you look at the typical plot of the distance, force versus distance plot. So, here this is the equilibrium position of the atom, and the atom may be sitting here, which will give you basically a little bit lower Young's modulus. So, this is a valid case in case of amorphous material. Amorphous material also shows lower Young's modulus because of the non-equilibrium position of the atom, and therefore, very similar situation also people observe in case of nanomaterial too. Now, the question here arises, if I keep on decreasing this grain diameter or size, does hardness increases continuously as per Hall-Petch equation? Let us have a look at the right hand side plot. Here I have plotted grain size versus hardness. Okay. So, you can see that from a large grain size, this is actually 100 nanometer, this is 1 micrometer and this is 10 micrometer. Okay. So, if you decrease the grain size, then it increases, but after that it does not increase. So, there is a breakdown of this Hall-Petch equation. So, as per Hall-Petch equation, if we decrease grain size, the strength should increase, sigma 0 is the lattice friction stress as per Hall-Petch. So, this is an example of a nanocrystalline copper. Now, so people try to understand, is it the real situation or some other mechanism is involved with that. So, in case of any bulk metallic alloys, in a grain, let us say a coarse grain microcrystalline sample, where there are immobile dislocation, means dislocation that cannot move, and there are mobile dislocation which are lying on a glide plane, where dislocation can easily flow and provide us some plastic deformation. However, stress required to initiate plastic deformation is the measure of the yield stress, or let us say 0.2 percentage of the total dislocation density, that is like 10 to the power 12 meter square. So, that basically when it moves, the stress required to move that 0.2% dislocation, that gives us the yield stress. That is why we call it a 0.2 proof stress. That is the reason. Now, the mobile dislocation because of the dislocation climb or dislocation glide on a plane. Let us say if dislocation stop by a particle, then basically the dislocation may take and go into a different plane, so that they can move. Now, dislocation has to be generated in a grain which is a Frank-Reed source, typically explained as I have shown in the right hand side. So, this is a two pinning centers where dislocation are first present, and then you give some stress and then it bow out and then bow out and then bow out. Okay. So, this is requires some stress, and this stress could be measured with the dislocation node. So, this distance is basically the L is the distance here, and G is the shear modulus, B is the Burgers vector. Now, in any case, this L we can think about a very smallest size or the largest size. So, how large this L can be? If I have a microcrystalline sample, the L max will be the grain diameter, whereas L minimum in an is like 10 to 15 nanometer in case of a small nanometer size, right. So, in a nanocrystalline material, this less than 10 to 50 nanometer, this Frank-Reed source for dislocation generation become impossible, because dislocation itself is not stable inside a nanomaterial, that we have proved in the last week. You can remember, dislocation always try to go outside the grain and join at the grain boundary. Okay. So, this is a Frank-Reed source, and dislocation keep on generated in a microcrystalline sample like this way and bow out, and they goes for multiplication process, which gives us the strengthening. So, this is the example of a Frank-Reed source in case of silicon. Now, the hardness decreases with the decrease of grain size, but below 10 nanometer it shows a inverse Hall-Petch relationship, which we have shown you just few minutes ago. You see here. So, like a typical example or a schematic that is shown here, that below 10 nanometer there is a breakdown of such a situation, and this is called as a inverse Hall-Petch relationship. Okay. So, is there any mechanism involved in this? We have to think about this matter and try to learn what is this inverse Hall-Petch relationship is unique about. Is it a grain boundary process? We have known that for a higher temperature deformation, so near melting temperature, the strain rate is proportional with the volume diffusivity and its square of the grain diameter. Okay. Whereas, in case of cobalt creep, it is actually the strain rate dependent on the grain boundary diffusion and the d cube, okay, cube type of relation. However, this occur at a relatively lower temperature. So, grain boundary control this process, and in case of a ideal grain boundary mechanism, so if these are the grain and these are the region which is basically a large grain boundary region, if we simply put some stress, the grain become elongated, and this would be the ideal structure where the number and the arrangement remain unchanged. So, Nabarro-Herring creep is a very common phenomena which is near melting temperature, but we are talking about deformation of nanocrystalline material at room temperature only. In that case, people observe that there are some other mechanism may be involved, that was explained by Ashby-Verrall mechanism, that is called grain switching. Means the deformation can only be proceed when we have a grain which are oriented like this, okay, and this grain will appear in an intermediate step here and the finally like this. Does it only involve the stretching of this grain? No, the position has changed and also the orientation has also changed. So, this is a switching mechanism with grain with the newer shape and newer configuration, and this is explained with a strain rate proportional with the d, let us say 1 by d cube. Okay. Now, what about the real experimental result? The real experimental result says that the time of deformation with the indentation size, this is a typical Coble mechanism and this is the Ashby-Verral mechanism, whereas the experimental points are lying here. So, the mechanism in nanocrystalline material cannot be really explained with a creep type of behavior, rather it will mostly follow a Ashby-Verral type of mechanism, where the both grain shape and new configuration involved, along with one can think about some growth of the grain and the grain boundary sliding. So, the inverse Hall-Petch relationship we can explain in a minute, that there are two different processes. One is the dislocation based process, another one is the grain boundary based process. When the grain size reduces, the mechanism of the dislocation based process decreases, whereas below let us say 100 nanometer size, the grain boundary process actually increases. Okay. So, this is the strain rate, and below 100 nanometer, and this is a zone where these both the mechanism are valid. However, below 10 nanometer mostly it is a grain boundary process that I have explained here and schematically in this region. So, inverse Hall-Petch relationship is linked with the grain boundary process. Now, the last part of these mechanical properties are the superplasticity. What do we mean by superplasticity? It is basically a strain greater than 100%, smaller grain size can be preferred and it occur at a higher temperature above 0.5 melting temperature. I show you two example of nickel 3 aluminum, which is a ordered structure with a 80 to 100 nanometer grain size, and titanium aluminum vanadium with a 30 to 50 nanometer grain size. You can see the strain is very high, it goes above 1 means 100%, and this is the stress level, and so material has flow occurred around let us say 920 or 950 K. Now, for getting such kind of superplasticity, people observe that the strain rate is proportional, inversely proportional with the d square, where the sigma to the power n is equal to 1 for a grain boundary or diffusion and 2 is for a dislocation based process. But so far from our discussion, we have seen that these in case of nanomaterial, the grain boundary sliding is one of the very dominating, and grain boundary process is very dominating. So, if I reduce the size of the grain to a nanometer, the superplasticity should exist. Okay. Now, so superplasticity in nanocrystalline material is observed at low temperature than their coarse grain analog. So, we can get very large plasticity in the nanomaterial, but mostly the experimental result shows that nanomaterial are very brittle in case of metals and alloys. But this is not linked with the material, rather I would say it is important to process the material properly. So, in case of such superplasticity often observed in the transition region from a dislocation to a grain boundary process, which I explained in the last slide. Now, is it true in case of ceramic, which never show any plastic strain in a uniaxial stress strain plot? See, here we have taken a tetragonal zirconia, which is nanocrystalline of 45 to 75 nanometer with a density very high, let us say relatively high compared to other material, and we have stabilized the tetragonal phase using 5% yttria. At this temperature of 1330 or 1400, we get such a large plastic strain, where ceramic material does not show any plastic strain at all. So, nanomaterial can show a large plasticity if the material can be processed and could be densed. So, that is basically the primary issue of getting plasticity or superplasticity in a nanostructured material. So, the common problem is the strength, whereas there is a flaw present that scales with the flaw with c to the power 0.5. So, that is the flaw size. Also appearance of low density, or let us say grain growth and processing related issues. So, so far we understood that the nanomaterial could give us unique properties in terms of the mechanical properties, strength, plasticity and so on. However, processing should be improved in order to achieve the best properties from the nanomaterial. We will discuss other properties or other mechanical properties, let us say in a polymer and so on in the next class. Thank you very much.